Hey everyone. So today we're actually starting to talk about functions, and that's assignment 32. I want to also look at things we do with function notation today, but first let's start with some vocabulary in our Bell work. Please define domain, range, independent variable, dependent variable, and what does it mean if a relation is a function? So here's y equals x squared. This relationship is a function, but this relationship is not a function. Okay? So take a moment to define these. We've talked a little bit about domain, so you should be able to say something there, but maybe not, and come back when you have questions or are done. Okay, welcome back, everyone. So domain is the list of all possible inputs for the independent variable. It's all the stuff you can plug into the function. Whereas range is the list of all possible outputs or dependent variable values. Okay, independent variables, that's where you plug in inputs. And dependent variable is the variable for outputs. Okay, so domain, inputs. And when we say list, I mean write in interval notation. So the domain is bracket 2 to infinity for y equals square root of x plus 2. No, x minus 2. Yeah, so if I have to say domain of this, it's going to be this. The range, however, it's all the possible outputs or y values. And so when I think about this graph, for example, this is y equals x squared minus 4. Okay, so is there any restriction on any x value that I can plug in? No, I can plug in positive numbers and square them and take away 4. I can plug in 0 and square it and take away 4. I can plug in negative numbers, square them and take away 4. All right, so domain then goes from negative infinity to infinity. But the range, well, I can't generate all the possible y values. This y value here is the lowest y value. And then if I look across and look, all these y values are going to be covered by different x values going into that function. So I think my domain starts at negative 4 and goes to infinity. Okay? So domain, all the inputs, range, all the outputs, independent variable, that's where I plug stuff in. Dependent variable, that's where stuff poops out. Now, what about function? I hear a lot of students saying 1 input for every output. But yeah, I always struggled with this, and maybe it's my dyslexia, but I always struggled with this definition. So let's see if we can come up with one that makes a little more sense. And I'd like to be able to determine whether something is a function or not by looking at a table, at a graph, and looking at some algebra stuff. Okay? So each input goes to only one output. I think you're gonna find that's more successful for you. So let's look at some tables. X, f of x, I need to call that y, x. Okay, so which of these, if any, are functions? According to each input goes to only one output. Well, this input only goes to 5, and this input only goes to 6, and this input only goes to 7, and this input only goes to 8. So that is a function because each input goes to only one output. But here, the input of 1 goes to first 3, and then to 4, and then to 5, and then to 6. So this is yes, a function. This is no, not a function. Input goes to only one output. I see that the output is repeating, but not the input. And that's what it says here. Each input goes to only one output. This input only goes there. This input goes there. Here, one went here, and here, and here, and here. Okay, so this is yes, a function. Okay, so now we have some ideas based on looking at a table when we can know whether, from a table, whether the relation is a function or not. So what is it that we see here? Each input, if I have repetition in the domain, then not a function. Okay, so I don't see any repetition in the domain of these. That's why these are functions. I do see repetition in the domain here. That's why this is not a function. Let's take a look at the graphs of each of these and see if we can come up with some sort of graphical understanding. Okay, so that is a function. And then here, 1, 3, 1, 4, 1, 5, 1, 6. There we go. Doink. That is not a function. And then our last one, 1, 3, 2, 3, 3, 3, 4, 3. Okay, so what can we see here? These are functions. This is not a function. Does anyone remember the graphical definition we had, or the graphical technique we had for determining whether the graph represented the graph of a function or not? That was the vertical line test. Not line, but line. Vertical line test. If a vertical line can be drawn through the relation so that the line crosses the relation more than once, then the relation is not a function. All right, so if I draw a vertical line anywhere here, I only cross once, so that's yes, this is a function. And over here, any vertical line I draw only crosses once, so this is yes, a function. But here, the graph is a vertical line, so that's no, not a function, because my vertical line crosses through all these different y values. All right, said a different way, if I had y equals x squared versus x equals y squared. So here, I can draw any vertical line, and I always cross just once. Yes, function. But here, I know there exists one place where I can draw a vertical line that only touches twice, but that's not what our vertical line says. It says, can you draw a line anywhere where you cross the relations graph more than once? Yeah, I got that here. And so this is not a function. This is not y is a function of x. Okay, so not a function. Vertical line test shows me clearly whether something is or is not a function. Great, so now we have a tabular way of doing this and a graphical way. And then, I want to take a look algebraically for a moment. For example, y equals 2, y equals 2x plus 1, y equals x squared plus 2x plus 1, y equals square root of x, y equals absolute value of x. So, we've got a linear function, we've got a quadratic, square root, absolute value. What do you know about the graphs of all of these? And that's really the way I want to answer this question algebraically. Someone gives me a function, but what I start thinking about is, what does that look like? Well, it looks like the horizontal line y equals 2. Well, that passes the vertical line test, so that's good. What about this one? Y equals 2x plus 1. Well, that's a linear equation with a slope of 2 and a y-intercept of 1. Can I draw a vertical line here that crosses more than once? No. So this is also a function. Here I've got a parabola. This is the same as x plus 1 squared. And from our transformations, we know that that shifts the graph left 1. And again, no problem. That's going to pass. That's a function. Square root of x. Well, I know the square root of x has a restricted domain, but that doesn't mean square root of x isn't a function. Here's my square root of x. 0, 0, 1, 1, 4, 2. Sure, look, vertical lines only touch once. And that's the same here with absolute value of x. So I kind of want to say that almost everything we work with, y is a function of x, and that we have a function here. There are some cases that are not functions. I mean, all polynomials of x will be functions. These are not functions. Y is a function of x. So this is x equals y squared. and x equals absolute y. So when I see these things algebraically, I say, no, that's not going to be a function of x because I get two different y values for this one x input. I get one negative 1 and I get one positive 1. Because I have that repetition in the domain going to two different outputs, this is not a function. All right, functionness. Let's move on. Let's move on to function notation now. Actually, I want to take a step before we do that. I've noticed recently that some students are having difficulty, this comes up on the ACT a lot, solving for the designated variable. Okay, so I've got a equals s squared. This is the area formula for a square. That's the side length of the square. Solve for s. Well, that should be pretty straightforward. Right now, we've got s squared, and I need to get rid of that squaring. I remember that square root will get rid of squaring. And since I can't, since the side length is always positive, I won't, even though I normally nag you about, hey, if you're taking the square root of both sides, make sure you put the plus and minus down. Yeah, I'm not going to have a plus and minus here because it doesn't make sense to have a negative area or a negative side length. So I'm going to end up with a square root of a equals s. So I have solved this equation for s. Okay, how about area equals 1/2 base times height, and solve for height. Can you do this one? If you can, pause the video, give it a go. Okay, welcome back. So I'm trying to get h by itself, and I see that attached to that h is a b and a 1/2 that I have to get rid of. Now, many students do this. And that's not wrong. It's just, I don't like having that fraction there. So I would probably do this problem a little differently. A 1/2 b h. Still solving for h, but I'm going to get rid of that 1/2 by multiplying by the reciprocal. Then those go away, and I have 2a equals bh. And then to get h by itself, and these are attached with multiplication, I better divide. And so I get that h equals 2a over b. And I think that's tidier than this. I wouldn't mark this wrong on a test. I would just smile when you did that. All right, so how about v equals 1/3 pi r squared h? How about you solve this for h? Why don't you pause the video and give this one a try? So again, I like multiplying here because now I don't have a fraction to contend with. And I see that the pi and the r squared and the h are all attached with multiplication. So if I want to get rid of everything but the h, I have to divide by everything but the h. So 3v over pi r squared is h. Oh, did I say h? Sorry, I meant r. Can you solve this equation for r? Why don't you give it a go and come back in a minute when you're done. Okay, so yeah, again, I'm going to multiply by 3. And now we're solving for r squared, so I'm going to divide by pi h. But I still have r squared equals 3v over pi h. I'm not done yet because this says solve for r. So that's right, I need to take the square root of both sides. Do I have to worry about the plus and minus here? No, I don't. R equals square root 3v over pi h. Great. Next, how can we determine if y is a function of x? You know, we just said a few minutes ago what it meant to be a function. No, no repetition in the domain. What else? Passes the vertical line test. Okay. We also know that all polynomials are asterisks are functions. And all polynomials are functions. Now, I've got an asterisk here, and I want to clarify this statement. So if I have something like y equals 3x squared plus 4x minus 7, that's a polynomial. That is a function. But if I have x equals 3y squared plus 4y minus 7, it's still a polynomial, but it's not a function anymore. So I kind of want to say here all polynomials where the independent variable is x. Those are all. Certainly, virtually everything that we have graphed so far this year, y is a function of x. Well, let's take a look at these two exceptions that we talked about before. This is x equals y squared, and this is x equals absolute y. So whenever I see a y squared or an absolute y, even if I saw something like and that would be x equals y times y squared minus 4, for example. -2, +2, and 0. Yeah, that definitely isn't passing the vertical line test. If I distribute, it's definitely a polynomial, but not a polynomial of x. And that's what this says. Y is a function of x. This is the independent variable. And this is the dependent variable. And we say this is the dependent variable because the value we get here depends on what I plug into for x. And that's why x is the independent variable. I can plug any number within the domain in there, but the y value that I get depends on what goes in for x. So see y squared, you see absolute y, not a function. Okay? So let's go through some of these. How about y equals 2x minus 1? And what I'd like you to do is look at the algebra and think, is this a function of x or not? Is y a function of x? And the answer here, 5, 4, 3, 2, 1, is yes. Did you think about it graphically and say a linear equation, no worries, always going to pass the vertical line test? Did you think about one input going to only one output? Doesn't matter, it's all good. How about y equals -3? Oops, no it isn't. It's -3x plus 2y equals 12. 5, 4, 3, 2, 1. Sure, this is just the standard form of the equation of a line. And when we see standard form like this, we know we're talking about a linear equation. And yes, this is a function of x. This certainly passes the vertical line test. How about y equals absolute x minus 4? Is that a function of x? 5, 4, 3, 2, 1. So according to my graph of this function, yeah, each input, that x value there only goes to one output, that x value there only goes to that output. So this is yes. How about x equals 2? Yes, that is a line, it's not a point. If it were a point, I'd have written it as an ordered pair. All right, so what do you think here? x equals 2. So, well, you know, some people like using a t-chart here. So x, y, x equals 2. Doesn't matter what y is, x is petulantly just going to say, I'm 2. So, do we see repetition in the domain? Sure do. That 2 goes to all kinds of y values. So this is not a function of x. This is not y is a function of x. This is not that. This fails the vertical line test. No good you. Okay, and what about this one? X minus y squared equals 1. Is that y as a function of x? No, no, this one isn't. No. You know, I could always solve for y equals x minus 1 equals y squared. And then when I take the square root of both sides, oh look, now I do have to remember the plus and minus. And because we're fabulous transformation graphers, we know this is positive square root of x minus 1, and this is negative square root of x minus 1. And notice we fail the vertical line test. So no, I see that y squared. I don't need to go any further. Y is not a function of x as long as I see a y squared. What about this one? X minus 1 squared plus y plus 2 squared equals 9. Is y a function of x here? Well, think about what you're looking at. You're looking at a circle whose radius is 3. Does that pass the vertical line test? No, it does not. Look, I see a y squared. Not going to happen. How about x equals absolute y minus 1? 5, 4, already, is it in a function or not? 3, 2, 1. So it's that absolute v rolled sideways. And see how at x equals 0 we have two different y values for the same input. Not a function of x. Okay, I mean I could say here x is a function of y and pass the horizontal line test. But no, this is not y as a function of x. Okay, so let's evaluate some functions. Actually, let's get rid of that one. Evaluate functions. Okay, so given f of x equals 2x squared plus minus 3x plus 2, and then told find f of 1. Do you remember what you do to find f of 1? Sure. See how there was an x there and there's now a 1 there? That means I'm replacing all the x's over here with 1's. 2, 1 squared minus 3 times 1 plus 2. 4 minus 3 is 1. Okay, how about f of 2? How will you do that? That's right, I would plug a 2 in for all the x's of f of x. 4 times 2 is 8, minus 6 is 2, plus 2 is 4. So f of 2 equals 4. And remember, when I see f of 2 equals 4, I'm thinking about that's my input and that's my output, which means I could always write the ordered pair 2, 4. Okay. Now how about this? F of negative 3. I know, right? 2, negative 3 squared minus 3 times negative 3 plus 2. Yeah, same. I'm replacing x with negative 3. And so I get 18 plus 9 is 27 plus 2 is 29. But what do I do when I come to f of triangle? Yeah, no difference. See, x is gone and triangle is there. 2 triangle squared minus 3 times triangle plus 2. There's f of triangle. Now, with that in mind, what about f of x plus h? What am I supposed to do there? Don't tell me you don't know. Come on, what did we do in the last problem? So when I saw f of negative 3, I plugged in negative 3 in for all the x's in f of x. When I had f of triangle, I have to replace all the x's in f of x with triangles. So when I see f of x plus h, I'm supposed to replace all the x's in f of x with x plus h's. So that's going to look like this. Great. Now, how about this? Remember, this is not just x squared plus h squared. This is a foiling opportunity, okay? Foiling 2x plus h times x plus h minus 3x. And oh my goodness, don't forget to distribute that negative to that h as well. All right, now here I've got some foiling to do. X squared plus 2xh plus h squared minus 3x minus 3h plus 2. I'm going to distribute that 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 2. That's f of x plus h, I think. Let's just check. Were there any like terms to combine? Well, here's xh and that's x, so I can't combine those. Here's h squared and h, and I can't combine those. So no, that's all I've got. All right. So now, let's take this a little further. Now I'd like to do f of 1 minus f of 3. How do I find that out? Well, I have to first find f of 1. Remember, f of 1 was where we plugged a 1 in everywhere. And we ended up with 1. And f of 3 was where we plugged in a 3 everywhere. Oops, sorry, meant minus 3. Plus 2. And what did we come up here? 18, 27, 29. So I know f of 1 is 1. I know f of negative 3 is 29. And so here, I'm going to have 1 minus 29. Right? F of 3 was 29. F of 1 was 1. And I want to subtract those two numbers. Negative 28. Okay. What about f of x plus h minus f of x? Well, that should be easy because we found f of x plus h, and wasn't that 2x squared plus 4xh plus 2h squared minus 3x minus 3h, don't forget to distribute that negative, plus 2. That's f of x plus h. We just did that. And f of x, well, here's f of x, 2x squared minus 3x plus 2. That's f of x. And now, what am I supposed to do? I'm supposed to subtract 2x squared minus 2x squared. There's nothing to cancel with this. There's nothing to cancel with that. Minus 3x minus a minus. Minus a minus is plus 3x. Minus 3x plus 3x. No, that goes away. Then we have a minus 3h. The 2's cancel. And there we go. That's f of x plus h minus f of x. Great. All right, the last thing I want to look at with this particular f of x is f of 1 minus f of negative 3 over 1 minus a negative 3. Hey, and by the way, while you're evaluating that expression with our f of x, will you please tell me what that represents? All right, so f of 1 was 1, f of negative 3 was 29, and we have 1 plus 3. So I get negative 28 over 4, or negative 7. Yeah, so what is negative 7 in this problem? What does it represent? Well, remember, this is the slope formula. Remember, we've got ordered pairs. 1, 1, negative 3, 29. And so I'm doing y2 minus y1 over x2 minus x1. This represents the slope of the line from -2 to 1. Okay, this is, and if we had some units here, we could say that was an average rate of change. The slope between 2 points on a graph is our average rate of change. All right, so now I've done that. Why don't you do these? F of x equals, nice and gentle, 3x plus 2. A, find f of 0. 5, 4, 3, 2, 1. 3 times 0 plus 2 is 2. B, find f of -2. 5, 4, 3, 2, 1. That's right, 3 times -2 plus 2 will be -4. No problem. How about C? F of 3 plus h. Oh, okay, so that's 3 times 3 plus h plus 2. That's going to be 9 plus 3h plus 2, or f of 3 plus h will be 11 plus 3h. Nice. Now, if I take this further, I could ask you about f of 4 minus f of -1. Will you please find that? Okay, so f of 4, 3 times 4 plus 2, that's 12 plus 2 or 14, minus f of -1. 3 times -1 plus 2 is -1. Don't forget this minus. So I end up with 15. Nice. How about this one? F of x plus h minus f of x. Can you please do that one? Five, 4, 3, 2, 1. Okay, so f of x plus h is 3x plus h plus 2 minus f of x. It's really important to distribute this negative to that 2. You're going to get it wrong if you don't. Any like terms to combine? Sure. And so we end up with 3h. Turns out this is very important for calculus when we get there. So, be thoughtful about that. So, how about this last one? G of x equals 1 over x plus 2. All right, so if I were to do g of x plus h, that would be 1 over, I'm replacing this with that, x plus h plus 2. That's not so bad. Great. With that in mind, what about g of -3 minus g of 0 over -3 minus 0? Will you please do that one for this g of x? Five, 4, 3, 2, 1. Good. So I need to find g of -3. 1 over negative 3 plus 2, or negative 1. I need to find g of 0. That's 1 over 0 plus 2, or minus 1/2 over negative 3. So that's negative 1/2, or negative 3/2 divided by negative 3 over 1. I remember Mrs. Rowan teaching me when you're dividing with fractions, you want to flip and multiply. So these cancel. Negative times negative is a positive, and I end up with positive 1/2. Okay, last one. How about g of 2 plus h minus g of 2, given, remember, that g of x is 1 over x plus 2. Okay, please find that. 5, 4, 3, 2, 1. Okay, so g of 2 plus h is what we get when we plug in 2 plus h for all the x's and then g of x, which is 1 over 4 plus h. And to find g of 2, I have to replace all the x's with 2's. 2 plus 2, 1/4. And now you're asking me to subtract. So that's 1 over 4 plus h minus 1 over 4. You know, it's funny because I also remember Mrs. Rowan saying, hey, make a common denominator. So my common denominator is 4 times 4 plus h. And on top, what do I have? 4 times 1 is 4. Then there's the minus sign. And then we're going to distribute this 1 and that negative to each of these things. And so I have that. Can we tidy that up? Sure. These 4's cancel. So we have minus h over 4, 4 plus h. That's g of 2 plus h minus g of 2. Turns out that's terribly, terribly important for us to be able to do in calculus. All right, so we've evaluated functions. What about evaluating piecewise? We've graphed them, now I want to evaluate them. So let's say that f of x comes in 2 pieces, negative 2x squared plus 4, comma, x greater than or equal to negative 1, and negative square root 1 minus x plus 2 for x values less than negative 1. All right, and what am I looking for? I'm looking for f of negative 2. Do I plug a negative 2 in for both of these? Well, that's the most common mistake that students do on the test. And I think it stems from not paying attention to this. These are domains. Okay, so it looks like this down-pointing parabola, but only for x values greater than negative 1 or equal to. And here's an upside-down reflected square root graph that's been shifted up to, but only for x values less than negative 1. So where is negative 2? Is it x is greater than or equal to negative 1, or is it x is less than negative 1? Well, when I think about negative 2 on a number line, it comes to the left. And I know the thing on the left is smaller than the thing on the right. So this is smaller than that, which means this is my domain. And since that's my domain, I use this piece. Negative square root 1 minus a minus 2 plus 2. That's negative square root of 3 plus 2. There's f of negative 2. Okay? What about f of 0? Would you plug that into both of these? No, why not? Right, because 0 is greater than or equal to negative 1, and so you can only plug in here. Negative 2, 0 squared plus 4. Well, 0 squared is 0 times negative 2 is 0 plus 4 is 4. There you go. And f of negative 1, well, equals negative 1. I use that piece. And so I end up with negative 2 plus 4, or 2. Okay, so we can evaluate these functions. Well, I feel like I did most of that evaluating, so maybe you should do this one. How about f of x equals 2x squared minus x plus 1 for x is less than 1, and negative x plus 1 squared plus 3 for x is greater than or equal to 1. Okay, looks like an up-pointing parabola for x values less than 1. Looks like a down-pointing parabola for x values greater than or equal to 1. So will you please evaluate this function, f of 2? I'm sorry, f of 2. Do I plug a 2 in for both of these x's? No. Then in which? Where should I plug that in? That's right. Here, 2 is greater than or equal to 1. So I'm plugging in my 2. I'm getting 3 squared is 9. Negative 9 plus 3 is negative 6. How about f of negative 1? Where do I plug in that negative 1? Negative 1 is an x value that's less than 1, so I'm going to plug in here. Negative 1 squared minus a negative 1 plus 1. So we get 2 plus 2 plus 1, or 5 for f of negative 1. And finally, what about f of 1? Well, f of 1 is, could be equal to 1. 1 plus 1 squared plus 3. 2 squared is 4. Negative 4 plus 3 is negative 1. All right, that's our review of function notation and how to use it, and even what is a function. I hope this helped, and you should try the homework, and I'll see you in our next Zoom. All right, take care.